All right, 8.2, the title is Integration by Parts. So what I want you to think about is the fact that when we do derivatives, we have a lot more properties than when we've done antiderivatives so far. In particular, there's 3 types of derivative rules that we haven't had anything like them much at all. Those are the product, the quotient, and the chain rule, right? Product rule, quotient rule, chain rule. Chain rule kind of has a little bit like the U substitution, so it's got a little bit of that flavor in reverse. But product rule and the quotient rule have nothing. We have not had anything that looks like sort of an inverse of that, right? Like going backwards. So section 8.2 is the first place where we're going to encounter a possibility of something that looks like that in some cases it will allow us to go backwards. So take a look first at the way, just a second. Okay, let's try again. So we're going to think about the product rule as you know it from a derivatives standpoint first. We're going to write it in a little bit of a different way. We're going to use these things called U's and V's, and it's just standard notation for doing integration by parts, so that's why we're going to use it that way. But if we have the product of U and V, and these are functions of X, okay, U and V, then the way that the product rule works is we write one of them down. I usually write the first one down first just as a U, and we take the derivative of the other piece, so it's V prime, and then we add that to the opposite. We write the other one down, V, and we take the derivative of, in this case, the first one, U prime. The order of this doesn't matter in the slightest, so we can switch it because addition is commutative, right? We can switch the order of each of the multiplication factors. So instead of writing U V prime, I could write V prime U. That's fine. So there's a lot of flexibility in how these can show up. If we go backwards, however, and we take that expression, and then we take the antiderivative of it. So in other words, we go up to where we started here, and we do the integral in all 3 of these pieces like this. Then the integral on the left is very nice because the integral symbol and the prime symbol just cancel and I get back to UV, right? You take the derivative, you take the antiderivative, you're back where you started with. That's the idea. But the pieces on the right don't work that way. They don't have a backwards kind of I'm just going to cancel a piece out. So when I take the antiderivative of U V prime, that becomes the antiderivative of U dV. dV meaning derivative of V. And then the antiderivative of V, du. Okay? I'm not going to ask you to repeat this process. I just want you to see where it comes from once so that you know where this is sort of occurring from. So this process, and then actually sort of sliding some things around, is actually what gives us the formula for integration by parts. So if we were to take now this piece right here, and we were to subtract it to the other side and then flip the equation around, we would have this formula down here. So the integral of U dV is equal to U times V minus the integral of V du. So all integration by parts is, and it's not able to be used on everything, right? Like that's not the way this is going to work. That's what chapter 8 is such an interesting beast of a chapter, is that we've got all these techniques that don't all work in any given situation. Some work in some place, others work in another place, and sometimes nothing works at all, okay? So we have to try and sort of flesh out what's going to work where. But when integration by parts works, this is how we use it. We find the integral of something, and it's going to equal uv minus v du. So let's actually write down a few steps, and there's just a couple, for how we go about using integration by parts. And then after you see one used, it'll sort of kind of start to piece together, okay? So some guidelines for choosing u and v. Typically, we let dv be the most complicated part that fits the integrand of a basic integration rule. Right? It's the most complicated thing I can take an antiderivative of. That's what it is. What is the hardest thing in here that I can still take the antiderivative of? That's usually what I let dv be. And then u will be the function, the portion, that gets easier as you take derivatives. So what do I mean by that? Well, let's take, for example, x to the 6th. If I take x to the 6th and I take the derivative, It gets easier as I go because the powers go downhill, right? It decreases in power. But there are some things that get messier as I take derivatives for them, or at least they don't get any easier. Trig functions are a really good example. Derivative of sines cosine, derivative of cosine's negative sine, it doesn't change in its complexity. Okay, so not all functions have this property. Now, these are some guidelines. Notice, guidelines means this isn't how it always works. This is sort of our best guess of what we're going to try, and we're going to see what happens, and sometimes it's still going to not work for us. They're guidelines. So, we definitely need to see an example, don't you think? Absolutely. Oh, there's one more thing that you probably should put in here. I don't have it listed, but it's probably worth mentioning, is that if you have the natural log of x in something, that must be, like if there's just a natural log x in there, not natural log of x quantity squared, just natural log of x, it must be u. And the reason for that is because of the same thing we encountered back in chapter 5. We don't have a definitive antiderivative form for natural log of x. So I can't let that be this dv thing that I'm going to take an antiderivative of when I can't take an antiderivative of it. Okay? We're going to encounter that in the first example. Okay, so here's an example. On A, we see that we have a natural log of x, right? And based on what I just mentioned in the last slide, we know that that natural log of x is going to have to be the thing that we're going to take the derivative of. So here's how we're going to set this up. We're going to set this up. There's lots of patterning kind of ways to set this up. I'm going to do it the way that I am most comfortable with it. And if you've seen it a different way or you want to do it in a different form, that's fine. I can work with that, okay? So we're going to identify u and du, and we're going to identify v and dv. And this is the patterning order that I always put mine in. U du, v dv. U needs to be, of the pieces that are here, there's this piece and there's this piece, and the dx is going to go over here at the end. Right? It's automatically going to associate at the end. I need to put the the x cubed and the natural log of x in one of these two locations. So I'm filling in the top left to the bottom right diagonal. Every time I'm going to fill those two pieces in, a u and a dv, okay? U is something that I have to take the derivative of, and it gets easier, or in this case, it's going to be the natural log of x because I can't do an antiderivative of it. The dv needs to be something that I can do an antiderivative of, and ideally it would be really nice if it got easier when I did so. This one's not going to do that, okay? I am locked in on this one. I do not have any choices. I have to put the natural log of x here because I can't take its antiderivative, which means by default, the x cubed goes here. Okay, everybody good so far? The diagonal is filled in. Every piece that followed the integrand sign is somewhere in my pieces I've put. They have to all go somewhere. You can't just leave something out, okay? It's all got to go somewhere. What happens next is we actually take derivatives and or antiderivatives of the pieces that follow. So u, which is natural log of x, has to have its derivative taken. So what's the derivative of the natural log of x? 1 over x. So we put 1 over x here. Okay, pretty good so far. The other side, I'm going to go the opposite way. I'm given, or I chose, I guess, kind of chose, had to choose, that the dv is x cubed. So when I take x cubed and I go back up, I'm doing an antiderivative. So what is the antiderivative of x cubed? X to the fourth over 4. And technically there's a plus c. We'll deal with all the plus c stuff later. We don't need to deal with it in the middle of the integration by parts. Okay? Everybody good so far? See where all the four pieces came from and how we figured them out. Okay, so you fill in this diagonal, right? That's what we did. That's where we started. Your answer then, what happens, is that you take this, and it's going to be, and I'm going to write it down at least for this first one, it's uv minus the integral of v du. That is what the previous slide said, 2 slides ago. So uv means that I take the product of what lies on top. Notice, I'm not taking the antiderivative of it. I'm just taking the product. I just multiply them together and I'm done with that piece. So I have u, which is natural log of x, and I have v, which is x to the fourth over 4. We'll write that a little bit cleaner in a moment, but for now, that's okay. I'm going to need a little bit more space. I'm going to shift this over some. Okay. Minus. Now we've got an integral of v. Well, v is the piece that's kind of messy looking, right? Hang on, did I write that down right? Yeah, I did. I just have my notes written down wrong. Okay. The v is the x to the fourth over 4. Right? X to the fourth over 4. And then the du, which is 1 over x. And then I still have a dx. Oh, I didn't write it in. I should put that there. This is also dx because I took the derivative. I left that off. So I'm looking, the yellow diagonal is where I sort of plug things into to start with. And then I use the top and I use this other diagonal second. The other diagonal is where I get the other pieces from. Okay, so on the first one, the first piece, I don't take its antiderivative. I'm just going to collect things and write them a little neater. I'm going to put x to the fourth in front, followed by the natural log of x and over 4. So that's a little cleaner than where it started. Over here, I have x to the fourth over 4 times 1 over x. Well, the over 4 part, I can pull that out in front. We've been doing that now across several sections, right? Coefficients or constants, can't decide which one I want to say, coefficients or constants that are multiplied are able to be pulled out in front. But what do I get when I have x to the fourth over x? That's just x to the third. I'm going to simplify it if I can. At this point, I can, so I will. So I have x to the fourth, natural log of x over 4, minus 1/4. And what is the antiderivative of x cubed? X to the fourth over 4. Okay? And that's when I'm going to put my plus c, because I took another antiderivative. So there's my plus c there at the end. The only thing I can do to simplify or clean this up any further is to combine those two 4's. So x to the fourth over 16 and plus c. Now consider for a moment. How could I make sure I was right?
Too close to derivative of u dv, so take derivative of u dv, and if it's correct.
Well, and not even just that. I would actually need the derivative of everything that I just got as my answer. So if this is the answer, right, if this is correct, and I wanted to verify that it really was, if I take the derivative of that, which is ugly, right? Yeah, it's not pretty. But if I take the derivative of that and I'm right, I will end up back where I started on the inside here. Okay? Because that's what inverse processes do. How do I know that 3 minus 5 is 2? Well, because I can go backwards and I can say 2 plus 3 is 5. How do I know that this is the antiderivative? Because I can take the derivative of it and get back where I started with. That's how I know. Now, we're not going to actually do it, but I want you to understand that that is the feature that we just found here, right? That is a true fact about what we just looked at. Okay, you ready for another one? Sure. All right. In some ways, this is easier than our last problem, and in some ways, it's a little bit more challenging. Okay, we're going to encounter a bunch of different examples that have their own sort of flair to them. This one is the integral of x cubed e to the x. So if you go back to this list of like guidelines or things to think about when you're making decisions, you notice one of them talks about being able to take antiderivatives of something easily, and the other one talks about things getting simpler when you take derivatives. So we kind of want to examine the pieces that we're working with, and there's two pieces here. Right, we have these two pieces. And by the way, we know we're doing integration by parts on these because they look like products. And they don't use U substitution or simplification with algebra. That's how we know. Okay, they look like products. So far, both of them have. And we can't do them with the techniques we've seen before. Okay, so both of these have the ability to take derivatives and antiderivatives without too much trouble. Agreed? E to the x is our favorite because what's the derivative of e to the x?
E to
E to the x. And what's the antiderivative of e to the x? E to the x. So he's great. So deciding what to do here is going to hinge upon what x cubed does, because e to the x could go in either location and it doesn't get harder or easier. But what about x cubed? If I take the derivative, it gets easier, right? And what I mean by easier is that the power goes down. Right? It goes from an x cubed power to an x squared power if I take the derivative. All right, everybody with me on that? Okay. So we're going to set this up, u du and v dv. Try to write a little bit small. We're going to go across the page kind of far on this one because we're going to do multiple steps of something. And I think it'll work better if it goes linearly. If it ends up going down another line, it'll be okay. But I think it works better a little bit better linearly. So if I go like this, I will have my x cubed here. I will have my e to the x dx over here. Now what is the derivative of x cubed? Oh, come on, guys. 3x squared. Thank you so much. 3x squared dx, right? Yeah. Okay, what's the antiderivative of e to the x? E to the x. We like that one. That one's great. Now take a look at what happens when I rewrite this. So I put things in along, and I'll keep using the same colors to try and draw our attention. I put things in along this diagonal. But when I put my solution down, right, the next step, I multiply the tops. So this will actually be x cubed e to the x minus the integral, and I use the other diagonal. So the other diagonal is now 3x squared e to the x dx. Now the part that's in front is sort of irrelevant. It's finished. The x cubed e to the x, I don't have to manipulate with it. I don't have to antiderivative it. I don't have to do anything with it. It's done. But the next part I'm going to have to take an antiderivative of, but what does it actually look like? It looks like the same thing. I mean, not exactly, but it's pretty close, right? It looks like another product. So you know what we're going to do? We're going to do it again.
We're just going to keep going down until we
Yes, we're going to keep going down until that piece that's the front, the x cubed, becomes the 3x squared. What's the 3x squared going to become? A 6x. And then what's the 6x going to become? A 6. Yeah, a 6. Okay, so u du. So the time, now I'm looking only at the integral part. The part at the beginning is just going to stay there. It's going to not move around. Okay, we're going to leave it alone. But this piece right here, and it will actually be a little bit easier for us. Well, one way or another, we need to be careful for the negative out front. I'm going to leave my negative out front on this one. Here's my 3x squared. Du would actually be 6x dx. And then I have my v dv. The dv again is e to the x dx, and the v, is e to the x. So as I rewrite this, and I'm not going to be able to go all the way across my screen. If you could, I can go. I did it across my paper just fine, but there's not enough space on the screen. The beginning part I said stays the same, and it does. It's x cubed minus e to the x. I'm sorry, times e to the x. Then I have a minus. And I need to make sure that I'm subtracting everything after that. We'll clean that up with the negative in a minute, but careful. So I'm multiplying across the top. So that's 3x squared e to the x minus the integral, and I multiply along the diagonal, the opposite diagonal, which is 6x e to the x. Here we go. Dx at the end. So I'm going to take that piece and I'm going to distribute through the negative like this. Okay, so negative is going to come through. So as I do that, I'm going to write another step down here. I have x cubed e to the x. I have minus 3x squared e to the x. And then I have plus the integral of 6x e to the x dx. Is everybody good so far? But we see we have another product, right? We're almost done. This is our last one we're going to see. But there is, in fact, a product here. 6x and e to the x. So I have another u substitution, u du, and a v dv. And they work the same way. U is 6x, dv is e to the x dx. Derivative of u is 6 dx. The antiderivative of dv is e to the x. And I'll rewrite. I have all the pieces at the front the same. Oh, that's not what I meant to do. So I have an x cubed e to the x minus 3x squared e to the x. And then I have this diagonal right here. And I have an addition sign now. Do you see this one? This one's actually a plus. The last one had a minus there. So I don't have to worry about my signs on this because it's addition. I'm going to multiply across the top. That's 6x e to the x minus the integral. And then the other diagonal is now just 6 e to the x, which is not a product. Not like what we mean when we say product for the purposes of calculus. When we say product in calculus, we mean a product of two things with variables in it. I recognize that 6 is multiplied by the e to the x, but one of them is a constant. So we generally call that a constant multiplier, not a product, to distinguish between the two. And the reason we do that is because it's easy to take an antiderivative when there's just a constant times something. It's when there's two variable quantities that make it difficult. So this first part now can be rewritten, and I actually just need the derivative of the second. So here's my answer down here so far. And then I have minus. Now what is the antiderivative of 6e to the x? Don't overthink this. 6e to the x, yes. 6 is a constant multiplier. He comes along for the ride. Antiderivative of e to the x is e to the x. And then we need plus c. Now, how often in u substitution or in integration by parts do we see this repeat over and over again? Not that often. But if I didn't show you one and you never knew that was a possibility, that would cause problems later, right? It is a possibility. And it happens generally in something that looks a lot like this. I have a polynomial piece that gets easier as I go, and I have some other piece that's either going to stay the same or that's going to oscillate. This one had an e to the x, but if I'd had a trig function and it's just going back between sines and cosines, we'd have the same thing going on here, right? So there's functions that have this sort of behaviors, and they do show up like this. Okay, changing again the process. So I do have a trig function on this one, but I don't have a polynomial for the other piece. So this is not just a variation of what I just did. This again has its own unique flair to it. And the reason it's going to happen is because both of these pieces, as we take derivatives and antiderivatives, never get easier. They never get harder either. They just oscillate, right? They keep changing a little bit. Signs just split between sine and cosine, sometimes there's a negative, sometimes there's a positive. E to the 2x is going to be itself over and over and over again, and then just the coefficient's just going to keep changing, right, by the power of 2. So this one is actually going to have its own oddity that shows up. Okay, so here's what we're going to do. We're going to let this go with u and du, setups the same way, dv, dv, and we fill in u and dv. And we're going to fill these in, and it kind of doesn't even matter that I'm doing it in the particular order I am. I just have to pick one because we know that they're just going to go back and forth. I'm going to choose to let the e to the 2x be my u, and the reason I am is because when I take the derivative of it, the 2 will come down as a coefficient multiplier instead of being a division factor. If I take the antiderivative of it, I'm going to get a division of 2, and I don't really want to involve the division if I don't have to. So it's a little bit cleaner to do it this way. The derivative of e to the 2x is e to the 2x times 2, because that's the coefficient on the exponent. That's actually a a chain rule involved there, dx. dv here is sine of x dx. So we need to know the antiderivative of sine. You have to be careful because sines and cosines oscillate, but sometimes negatives come into play and sometimes they don't. So it's going to be cosine, but is it going to be positive cosine or negative cosine? Negative cosine is correct. Negative cosine. Okay, so far so good. Okay, all that is going to allow us to do our next step. Multiply across the top. I'm going to put the negative in front, so this is negative e to the 2x cosine of x minus the integral, and then I'm going to multiply along the opposite diagonal that I put things in on. So I've got another negative, so negative. I'll cancel my negatives in a second, but I'm going to write it there for the moment so that if you're looking back later, you see where it went. Negative, and then I have 2e to the x cosine of x dx.
Oh.
Okay, so this negative is happening because it's part of the formula, right? And then the other one because it's part of the v. But they do cancel. So as we're sort of thinking about this, there's not going to be a negative over there. But if you notice, it didn't get any easier. I changed from e to the 2x sine x to e to the 2x cosine of x. And that is not just kind of like the last thing I did. I'm like, it's almost identical. Like it didn't even get easier. Like over here, it got easier, right? It went from x cubed down to x squared. There was hope at the end of the tunnel that it was going to actually go away at some point. None of these are going to go away. Let me show you what happens though. We are going to do another u du and a v dv, and we're going to set them up exactly the same way. E to the 2x, that's going to give me 2e to the 2x, sorry. I totally left my 2's off. There's a 2 right here. All right, so sorry. 2e to the 2x, and then when I take the antiderivative, or the derivative, excuse me, I'm now going to have 4e to the 2x dx. dv is now the cosine of x dx, and what is v going to be? What's the antiderivative of cosine of x? That one is going to be the positive sine of x. Okay, so writing down what we have e to the negative e, in the right order, negative e to the 2x cosine of x. And then it's going to be plus the diagonal across, or the line across the top. So 2e to the 2x sine x. And then minus the diagonal over here. So minus the integral of 4e to the 2x sine x dx. Yes, sir.
So since we get rid of those two negatives,
Mm-hmm.
is that why cosine of x is not negative anymore? Because in v in that.
Yes, I moved the negative to the front so that it would cancel with the other negatives. I clean up negatives as I go. It's really easy to get things all messed up if we keep the negatives when we can simplify
So you
them.
can simplify that.
Absolutely.
Go ahead.
Yeah, and if you had places where you could like simplify a multiplication by 2 and a division by 2, by all means, do that kind of thing. So you can clean things up as you go. You definitely should. It'll make it easier. I want to show you one thing that happened here. I actually want to write this like an equation. So here's where we are. Here's where we started. Correct? I think this is an equality that keeps going. If I rewrite this piece at the end with the 4 moved out in front, check out where I am. This and this match. Like I'm literally right back where I started. And while that looks like a bad thing, it's actually a really good thing. Okay? And the reason it's a good thing is because this is an equation. And you have all the properties you learned in algebra where like you can add something to both sides of the equation. You can multiply by something on both sides of the equation and it doesn't change the equation. Those are called multiplication or addition properties of equality. So why does it matter? Well, it matters because, and in fact, I'm going to do this, actually, let's just rewrite it one step here. So I'm going to rewrite the pieces that are before this. I'm going to cheat and copy paste, but what I'm going to do is I want to solve for the integral of e to the 2x sine x dx. I mean, that's the goal, right? I want it to say that piece on one side and something on the other side that has a closed form, right? That doesn't have any integrals in it. So what I can do is I can actually add 4 integral of e to the 2x sine x dx to both sides. Do I have space? I do. Okay. So if I do that, what am I going to be left with on the left? What happens here?
It's just gonna be 5.
Yeah, I have one of them here. It's not written in, but it is. It's one of them. And I have 4 of the exact same thing underneath. And I can add those together, just like it says x plus 4x, it'd be 5x, right? Now, it's a little weird looking, admittedly, but they are identical things. And so I can add them together. This will give me 5 times the integral of e to the 2x sine x dx. And it's going to equal those pieces that we had that would still be remaining on the right-hand side. Negative e to the 2x cosine of x plus 2e, was it 2e?
Yeah.
Yes. 2e to the 2x sine of x. Now, that's not exactly where I'm going to stop. I need to do one more thing. Any idea what it might be? I need to divide both sides by 5. The goal is to solve for this thing, right? I've consolidated them now. That's good. But I really want to solve for it. So I need to divide by the 5 that's occurring. So I'll divide each piece by 5. So the solution then is that the integral of e to the 2x sine of x dx is equal to negative, and I'm going to write it as 1/5. Negative 1/5 e to the 2x. You can write it over 5 if you want. Cosine of x plus 2/5 e to the 2x sine of x. So we have this one new tool, integration by parts, and we've seen 3 problems that are extremely different, right? They all work really differently, but they're all still using the same tool. Okay, ready for another one? Caleb's like, no, hold tight. What's your question, Caleb?
Do we have to do it twice in order to get to it, or can we have stopped at the first one?
We couldn't stop at the first one because they didn't match. At the first one, this piece right here had a cosine in it instead of a sine. So when this property shows up, it will show up after 2 iterations because that's how sines and cosines flip-flop. And this really only happens with sines and cosines. So if you're not seeing sines and cosines, you're not going to do this. It's not going to happen. Yep, Doe?
Just the answer, ends in plus c.
There's no plus c on this one because of the way that we, yes, there is. I'm sorry, I just left it off. I was like, where is my plus c? Yes, there should be because of the way we shifted things around. We still will have a plus c. I just left it off. We'll add that back in there. Each time along the way, we've avoided writing the plus c because we have to do another integration. And here we actually finished it in a slightly different way. So there is an integration constant of integration there, added c, that's showing up in each of the terms. We just kind of dumped them all together eventually. And thank you for noticing that. I definitely left that off. Good catch. Okay. Ready again? Okay. Now, this one almost looks like things we've seen before. And in fact, it looks like a product. So it does look like something we should be using an integration by parts for in this section, but it actually doesn't need integration by parts. It's showing up in this section because they want you to recognize that not everything that looks like products actually uses integration by parts. And you've seen some that don't. U substitution works for lots of things that look like products. That's the only tool you've had before now, except for like simplifying with some algebra or trig. So you've seen that happen. So what they want you to do is they want you to be able to build on your base of knowledge, not just say, now that I know integration by parts, every time I see a product, I'm going to use it. Okay? If you try integration by parts here, what you will find is it won't work. Everything will just keep getting messier. It never simplifies and cleans up. Nothing ever shifts around. It won't be helpful. The reason I mention this here, though, specifically is because it has a very interesting form. Now, we could actually do this with everything in Calc 1. Like this question could show up in Chapter 4, and we could do it in Chapter 4. We don't do it there because it's a little bit weird, and it's kind of just a weird situation, and shows up better in Chapter 8 because we're working with lots of weird situations. Okay? So let me show you how this works. We are going to want the problem is that what's underneath the radical has addition and subtraction. That's really the problem. And it's a linear term. So if I use u for what's underneath the radical and I take the derivative, I get something that seems like it's very unhelpful because the derivative is just 1, right? And that 1 is not the same as the x on the outside. So if you had done this before right now, or even right now, as you're looking at it, you might still be thinking, okay, well, u substitution doesn't work. I don't get the x, right? It doesn't look like it works. Here's the trick. Because I've created a value for u, I can rewrite this and we can solve it for x, okay? So if I solve this for x by adding the 5 to the other side, x is actually u plus 5. So here's why that's better. So I'm going to actually make the substitution, and you're going to see how it all cleans up and why that's better. Because it kind of seems like I'm just trading things off. Why do that? I've just changed a subtraction into addition. Why is that helpful? It's actually quite helpful. So the x on the outside is going to be replaced by u plus 5. The x minus 5 underneath is going to be replaced by u. And then I know that dx is going to be equal to du because that's what I found as my in-between step. The trade-off is that the addition subtraction is no longer underneath the radical. Okay, did I mess something up? Oh, it's supposed to say du. Yep, sorry. Moving too quickly, thank you. We'll get that fixed. Okay, so the trade-off is the addition subtraction, in this case ours was subtraction, that's underneath the radical is no longer under the radical, it's on the outside. And that is better. And here's why. I can actually rewrite this square root. In fact, I'll just do another step. I can rewrite the square root part as u to the 1/2, right? And because the addition subtraction is not under the radical, I have distribution properties. I can't distribute under the radical, but I can distribute over the radical, like outside of it, right? So I can actually distribute this u to the 1/2 to each of these values. So if I take u and I multiply it by u to the 1/2, what will I get? U to the 3/2. And then I add 5 u to the 1/2 du. And I can integrate. So what is the antiderivative of u to the 3/2? Okay, u to the 5/2, and then what did you have, Josh?
Well, it's 2u to the 5/2 divided by 5.
Good. Okay, so we've got a 2/5 out in front, or divided by 5/2 if you prefer, multiplied by 2/5. Our new power is u to the 5/2. What about u, the 5 here is going to stay. What about the u to the 1/2?
U to the 3/2 or 5u to the 3/2
Over 3/2, or if you would like to do it as multiplication, you can multiply by 2/3, right? Divide by 3/2, multiply by 2/3. And I have a plus c on the end. Do I have more space? I do not. Let me make this smaller. Okay, we're almost done with it. So this is a 2/5. U to the 5/2 would be the square root of u, but u is x minus 5 to the 5th, plus I now have 10/3, and I have a square root of u, which was x minus 5 to the 3rd, plus c. So how do you know when to stop? I think it's probably a good place to start at this point. This is a good place to stop. If the problem started out with radicals, the problem needs to end with radicals. So that's why I put it back in radical form, okay? If you've got a square root of powers, right, like this And technically, is there another way to write this? There is. I can simplify, not simplify, but I could at least change the way this is written because this is a power 5 and I've got a square root and I could change it. That doesn't make it any cleaner or better. It doesn't help us out to do that. If I had constants, right, if I just had like the square root of 2 to the 5th, we would definitely clean that up. Those are constants. But some of the things that we do with constants, we don't do with variable expressions. This is perfectly good place to leave this. Put it back in radical form, leave it alone. Okay? One more example. Are you ready? Okay. Last example for today, I think, isn't it? Yeah, it is. This one says to find the definite integral. That's not really a whole lot different, but what does it mean that is different?
It's between 2 points.
It's got a lower and upper limit of integration, right? This is the stuff we were doing in chapter 7 when we were finding, areas and volumes and things like that, right? Arc lengths and so forth. So we won't have a plus c at the end. At the end, we'll be evaluating. That's the trade-off. Okay, but all the other stuff works the same way. And in fact, it's kind of nicer than when we did u substitution, because in u substitution, you have to remember to turn the u's back into x's and then do the evaluation. You remember that? With integration by parts, while there is a u and there is a v, I don't ever actually change them in the problem to u's and v's, right? I'm just identifying them as a u or a v as an in-between step. So that's a little different. So taking a look at this one, what I want you to notice is that it does not look like there is a product. Do you see that? There's no product here. There is a natural log, and you do not have a form still, you didn't at the beginning of the lesson, and you still don't now, for finding the antiderivative of natural log. So while it does not look like there is a product here, there's going to be one. It's just not what you would have expected. So we're going to write this down as u and du. And as we've mentioned before, the u needs to be the natural log part. So it is natural log of its interior, which is 4 plus x squared. That is u. So what is left for there to be as dv? 1. Yeah, it's just plain old 1. So I say it's not very intuitive. It's not very exciting. It doesn't look like anything that's a product. And in fact, just a little bit ago, I talked to you about the fact that we don't really call this a product. It's a constant multiplier, right? But there's nothing else left for it to be. So it is what we're going to have there. Now, its antiderivative is easy. So what's the antiderivative of 1? That one's x. So we got that one for very easy. The other piece, though, is a little messier. Because what kind of a rule am I going to need to take the derivative of the natural log of 4 plus x squared? That's a chain rule. Very good. So what's the derivative of natural logs? 1 over x, which would be 1 over 4 plus x squared here. Okay, and then what? Times 2x. And we're going to put the dx on the end. Okay. We're hitting on just everything today, aren't we? Man, this is one of those comprehensive lessons that makes you think about all the things you've ever done in math in your whole life. And we're not done. All right, let's see what happens. Multiply across the top. Okay. You can leave the integration 1 and 0 on, those limits of integration if you want. I'm just going to leave them off for now as I work my way through because they're going to look a little bit funny as I go. So I've got x natural log of 4 plus x squared minus the integral, and I need the other diagonal space. So this other diagonal right here means I'm going to have a 2x squared on top, and I'm going to have a 4 plus x squared dx. Okay, so I multiplied the x in the place of v times the 2x, that's the inside part of the chain rule, and it's over that the 4 plus x squared. So we see where all the pieces came from. What do you notice about the power on top and the power on bottom? They're the same. So when the power on top and the power on bottom are the same, and if there's addition or subtraction in the denominator, which there is, If they're the same or if the top's bigger, we're in that situation of long division that I mentioned at the very beginning today, right? In 8.1. Said, remember that thing called long division? We need an example of it, because imagine you haven't done it in years, right? Probably not. It's not something that comes up very often. So let's take a look at this. We take the part that's on the outside, on the top, and put it on the inside, so 2x squared. And then it's being divided by what's on the denominator, which is 4 plus x squared. And if you don't like it written as 4 plus x squared, feel free to rewrite it as x squared plus 4. In fact, I think I would do that. So I'm going to do it that way. Descending order of exponents is a little easier to look at when we're doing long division. So here's the way long division works, okay? You ask yourself, it works this way for numbers as well. You just don't think of it quite the same way, but it does. You ask yourself, what do I need to multiply x squared by to get 2x squared? And the answer would be 2. It's not a very hard answer, right? We're going to put a 2 here. And then we're actually going to multiply that 2, not just by x squared, but by x squared plus 4, the whole thing. So 2 times x squared is 2x squared. 2 times 4 is 8. So it looks like this. But as with anything in long division, you're clear back to 3rd grade, what you do after you do that multiplication is you subtract. So we're going to subtract, and for the purposes of polynomials, it means changing all the signs. That's what subtraction would mean. The 2x squareds are going to cancel, and I'm going to be left with a negative 8. Okay, so everybody good? So this expression that I previously had that said x ln 4 plus x squared, that part stays the same. But the previous part that said the integral of 2x squared over 4 plus x squared will now be the integral of 2, and then it'll be minus 8 over 4 plus x squared dx. Now, part of that integral is really easy. And in fact, if you wanted to separate it, you certainly could. You could rewrite this and put a dx here. You could distribute the negative through, so this makes this a positive, and do another integral here. In fact, that's not a bad thing to do, right? Separate it into 2 integrals. And the reason the sign changed is because this negative out in front applies to everything inside. So it applied to the 2 and to the negative 8 over 4 plus x squared. Well, the antiderivative of 2, that's not a problem. What's the antiderivative of 2? 2x. Whoops, it's subtraction 2x. What do I do for 8 over 4 plus x squared? Look back at this list of things that I gave you you might want to consider these as things to do in 8.1. Yep, I was right. What does step number 3 or consideration number 3 say? Remember arctrig, because we never remember them, right? So here we have something that's got a squared on the bottom. Clearly, I can't do anything else with division. There's no u substitutions that are going to be helpful. I need to remember arctrig. So look back at your, I think it's your antiderivative sheet. Do you have your antiderivative sheet handy? Does anybody have theirs? Josh is like, nope. What are you talking about? Antiderivative sheet? I'm going to see what number it is because I don't remember. I have the ones I keep giving you guys. So number 20. Number 20 talks about finding the antiderivative of 1 over a squared plus u squared. Okay? And it gives us a form for doing that. It says that I'm going to do, the 8 in the front is just going to be an 8 in the front, so we'll ignore that for the moment. I'm going to do 1 over a. Well, that's 1 over 2, because this 4 right here is 2 squared. Agreed? So the a is 2 that it's talking about. So this is 1 over 2. And it's the arctangent of x, which ours is also x, over that same 2. And then we got a plus c at the end of all this. Oh, I'm not going to need my plus c's because I'm doing a definite integral. So I'm not going to need that. Okay. We're really close, at least in terms of the calculus part of this. So 4 plus x squared minus 2x. The 8 and the 1/2 will multiply to give me a 4. And then arctangent of x over 2. If this didn't have the limits of integration 0 and 1, we'd be done, but it does. So we need to evaluate this at 1 down to 0. And I sure hope I have more slide space. Oh, either way, I'm at the end, so we'll just put it here anyway. Okay, so if we evaluate this at 1, I have 1 natural log of 4 plus 1 minus 2 plus 4 arc tangent of 1/2. That's putting in the 1. Okay? We've gotten really good into a habit of thinking that putting in zeros always zeros everything out, and it doesn't always, right? It does a lot of times when we were dealing with polynomial functions, but this is definitely not a polynomial. On this one, oops, it's subtraction. We'll put in zeros. It does zero out the first piece. It's 0 natural log of technically 4 plus 0. And then it's minus 2 times 0. That's fine. But then it's plus 4 arc tangent of 0 over 2, which is 0. Okay, so that's what that looks like right now. Some of this cleans up, some of it does not. Okay, 1 times the natural log of 4 plus 1, that's natural log of 5. And we can't write it in any simpler way. Minus 2 is minus 2. The arc tangent of 1/2. So the arctangent of 1/2 is actually, it sort of feels like it should be on the unit circle. If it were arc sine, it would be. But it isn't. The arctangent values that we're able to find have radical 3s. So like radical 3 or radical 3 over 3. And they have 1s and 0s, I suppose, as well. This is none of those things. That's actually good news for this because that means that it's done. It's the arctangent of 0, or arctangent of 1/2. It doesn't actually simplify. Over here, this is 0. This is 0. And then the last piece we need to pause and actually think about. What is the arctangent of 0? Do you know? What is that?
It's either 1 or square root of 3.
Actually, it's not, but those are good guesses. It actually is 0. And I know I told you we want to be careful because it's really easy to think that they always are, and they aren't always. But if I'm on the unit circle at 0, whoops, and I want to have my sine over my cosine value or my y over my x value, what's y? It's 0, and x is 1, so this is 0 over 1, so it is 0. This is the answer that we're looking for in all of its glory. Can't be written any cleaner, and we're finished.